In 1964, Stephen H. Dole and Isaac Asimov got together and wrote a cute little book entitled, Planets for Man. Chapter 3. The Properties of Planets. General Planetology. About 50 years ago it was recognized by H. N. Russell and independently by E. Hertzsprung that the stars might be grouped into families according to their luminosity and the nature of their spectra. To illustrate the orderly progression and relationship of these two characteristics, they prepared versions of what is now known as the Hertzsprung-Russell (HR) diagram. The overwhelming majority of all stars fall into a straight diagonal line on the HR diagram. This line is the main sequence and the stars occupying it are our main sequence stars. The light of a star, or of any source of light, can be spread out into its component colors to produce a spectrum. The pattern of color, the existence and position of dark areas, representing light absorption, and bright areas, representing light emission, vary according to the chemical composition of the light source, its temperature, its motion, its magnetic properties, and so on. Almost all that we know about stars aside from position and brightness has been obtained through careful study of the details of their spectra. Since the time of this discovery, many general relationships among such factors as mass, luminosity, age, diameter, density, temperature, spectral type, composition, internal conditions, and nuclear reactions have been deduced for stars. Ideas are continuing to be developed about the evolution of stars and about the internal and external physical and chemical changes accompanying the aging processes. Ideas are being developed too about the modes of formation of stars, the relationships between members of closed double stars, the distribution of types of stars in galactic clusters, and so on. It is not necessarily true that all current ideas on these matters are correct, many in fact are conflicting. The point, however, is that general relationships of some sort do exist. The large luminous bodies of matter in the universe called stars or suns are not individually unique, they are not curious unrelated specimens that must be studied singly. Stars are instead recognized as members of a class of objects with group similarities. Individual stars differ in mass and age, but other observable properties seem to follow inevitably from these primary qualities, plus a very few others such as rate of rotation, propinquity to other massive bodies, and possibly original chemical composition. Stars can therefore be considered in groups, and all stars with a particular type of spectrum, for instance, can be expected to have many properties in common. Astronomers have been able to come to this conclusion because the number of luminous bodies individually detectable in the sky runs into many billions, and because out of these billions no less than 500,000 may be called well-observed stars. Consequently, we have available a large population to study and compare, to analyze statistically for number and distribution, to observe spectroscopically, and so on. Quite a different situation prevails when it comes to the non-self-luminous bodies in the universe. This class of bodies can be detected only through their ability to reflect light, or very occasionally through their gravitational effects on nearby stars. The members of this class that are known in some detail are therefore restricted to a few relatively small bodies within our solar system, bodies including those that are commonly called planets, satellites, and asteroids, or planetoids. Because the sizable non-luminous bodies of the solar system are so few in number, they have usually been treated as individual objects, each with unique properties, and they have been studied as such. Yet if some current ideas about the formation of stars are substantially correct, there are almost certain to be many more planetary bodies in the universe than there are stars. It is then to be expected that the class of planetary bodies could be subdivided into families or classified in a number of ways according to their physical properties and their positions with respect to nearby stars. From this point of view, then, the planets of the solar system might be regarded not as unique specimens but as members of large families of such objects in which the relationships between the definable physical characteristics would be found to follow certain general laws of nature. It is only because we have so few to study that these relationships have not become perfectly obvious. The word planetology has been used in the past to mean the study and interpretation of surface markings of planets and satellites. A broader term is required to cover not only the surface markings but all the physical properties of non-self-luminous bodies, whether they are a part of our own solar system or are orbiting about some other star. For this purpose the term general planetology is proposed and is defined here as a branch of astronomy that deals with the study and interpretation of the physical and chemical properties of planets. In this context, planets will then be defined as massive aggregates of matter that are not large enough to sustain thermonuclear reactions in their interiors. If they were large enough to sustain such reactions, they would become self-luminous and would then be classified among the stars. At present it is obvious that our knowledge of the underlying laws of general planetology must be far from complete. For one thing, some of the properties of the planets of the solar system, on which we depend for our starting point, are known only approximately. Our information is not reliable enough to be used as part of the firm foundation of the study. The density of Mercury, for example, has been reported by some observers to be as low as 3.7 grams per cubic centimeter, and by others to be as high as 6.2 grams per cubic centimeter. Numerous intermediate values have also been given. This variation in reported density is a consequence of the extreme difficulty of measuring with precision either the mass or the diameter of Mercury. If the diameter were accurately known, the volume of Mercury could be easily and precisely calculated. If the mass were also accurately known, then that mass divided by the volume would give the density. However, Mercury is too small and too difficult to observe near the glowing sun for its diameter to be easily determined, and the fact that it lacks a satellite deprives us of the surest method of determining its mass, which would be to measure the period of revolution of such a satellite about Mercury and its distance from the planet. The physical dimensions and densities of Uranus and Neptune are also known only approximately, while scarcely anything at all is known about Pluto. In addition, our current state of knowledge concerning the properties and behavior of ordinary matter under extreme conditions of pressure, as must exist in the interiors of planets, is still quite rudimentary. It cannot yet be said that we have anything but a fragmentary picture of the causes of mountain building processes, earthquakes and volcanoes, or of the structure of the Earth's crust, its mantle or its core. Finally, there are many areas of study in which the complete working out of all the effects that could take place is so extraordinarily difficult and complex when using present techniques that it is often necessary to simplify the problems greatly to handle them at all. A case in point is the current state of Earth meteorology. Great strides are being made in the understanding of winds, storms, precipitation, air circulation patterns and other atmospheric phenomena, but many questions still remain unsolved, the cause of the ice ages, for instance, to take a spectacular example, and most weather predictions must still be made on a largely empirical basis. How much more difficult would it be then to elucidate planetary meteorology in a completely general manner, taking into account every possible combination of atmospheric composition, planetary mass, surface gravity, rate of rotation, land-sea ratio, tilt of the equatorial plane, and so on. Despite all this, there remain certain overriding or dominant astronomical factors that permit estimations of the more general aspects, at least, of planetary meteorology. A knowledge of the relative universal abundances of the chemical elements, coupled with an understanding of the chemical and physical properties of the most abundant elements and compounds, permits us to make deductions as to the constituents that are likely to be part of the original makeup of a planetary atmosphere. Then too, the conditions necessary for the loss or retention of various gaseous atmospheric constituents can be estimated, and in this way certain sub-classifications of planets can be derived according to the type of atmosphere they eventually retain. The main objective of general planetology, in common with all science, is a fuller understanding of the universe in which we live. Some subsidiary objectives are to define the general characteristics of planetary systems, to gain a clearer understanding of the characteristics of habitable planets, and to obtain a more definitive estimate of the number of habitable planets in our galaxy, to indicate which of the stars in the neighborhood of the Sun would be most likely to possess habitable planets and what the probabilities of such possession might be, and finally to obtain a better understanding of our own planet and an appreciation of the combination of factors that makes the Earth a comfortable place to live. With all that in mind, we begin by turning to some of the general properties of the planets of our own solar system. The upper limit of planetary mass. It would seem natural to begin a discussion of the properties of massive aggregations of matter in the universe with a description of the modes of formation of the stars and planets. This subject is a controversial one, but the theories most commonly accepted nowadays picture the stars as originating by the slow gathering together, accretion, of dust and gas within clouds of cosmic matter, and planets as formed in a similar manner from the leftover matter surrounding the newly formed stars. The accretion hypothesis seems to account quite satisfactorily for most of the presently observed properties of the bodies of the solar system in a way that no other hypotheses do. Thus, without going into the minute details, about which there is much argument, we will assume here that the accretion hypothesis is correct and pass on to the solar system as it now exists. By far the most important basic property of large aggregations of matter is mass. The very distinction between stars on the one hand and planets on the other can be made to rest almost exclusively on mass. If the mass of a body is large enough, internal pressures within it will raise the temperature to the point of triggering and sustaining thermonuclear reactions in its interior. Such bodies will be stars. If the mass is not large enough to support such thermonuclear reactions, the body is non-self-luminous and is therefore a planet. All of the stars of which we have any observational knowledge are in the mass range from 0.04 to about 60 times the mass of our Sun. What's more, the vast majority of stars that we can observe fall into a much narrower mass range between 0.2 and 5 times the mass of our Sun. This limited mass range of stars was surprising when first discovered, but astronomer A.S. Eddington explains such a limitation on the basis of the balance between gravitational force tending to contract a large body and radiation pressure tending to expand it. Eddington defined a star as any aggregation of matter with a mass between 10 to the 32 and 10 to the 37 grams, that is from 0.05 to 5,000 times the mass of our Sun. He held that a body of less than 10 to the 32 grams in mass could not remain self-luminous as a star, and that an aggregation of matter exceeding 10 to the 37 grams in mass would blow itself apart by the pressure of its own radiation. If we reach below the minimum mass level for stars, we reach the region of non-stars or planets. Clearly there is some upper limit to the mass of a planet and some lower limit to the mass of a star, although the exact value of mass at which this transition takes place is not known at present. Indications are, however, that the transition region lies somewhere between 1,000 and 10,000 times the mass of the Earth. This may also be expressed as between 0.003 and 0.03 times the mass of our Sun, or as between 6 times 10 to the 30 and 6 times 10 to the 31 grams, the region just below Eddington's minimum. Unfortunately, no bodies with masses lying in this transition region are well known. Of the bodies of our solar system, the largest next to the Sun itself is Jupiter, which has a mass 317 times that of the Earth. It would have to be over 3 times as massive as that to fall into even the lower limits of the transition region. 3 other planets of the solar system are more massive than the Earth. Saturn has a mass 95 times that of the Earth, Neptune is 17.5 times the mass of the Earth, and Uranus is 14.5 times the mass of the Earth. All the other non-self-luminous bodies of the solar system are less massive than Earth. It is possible that increasing knowledge will not completely sharpen the value of mass at transition, that the dividing line between the largest planet and the smallest star may be inexact by its very nature, because minor effects are produced by factors other than mass. If so, there may even be overlapping, so that some large planets will prove to be slightly more massive than some small stars. Thus, if the rate of matter accumulation by a growing planet depends not only on its mass at the moment but also on the local density of unaccreted matter and the relative velocity of that matter, then it follows that 2 objects ending up with the same mass may have had quite different rates of growth. One planet surrounded by a low density of unaccreted matter would have had a slow rate of growth, permitting a longer time to radiate away the kinetic energy resulting from the accretion of moving particles falling into the planet. This might result in central temperatures not quite high enough to trigger off the thermonuclear reactions necessary for a star. If it had been surrounded by a higher density of unaccreted matter, it might have grown more rapidly, reaching the same mass but having less time to get rid of heat. It would then have reached the trigger point and become a star. A borderline class of objects might conceivably exist too, objects that are just able to trigger off thermonuclear reactions but lose this ability on the expansion that follows their rise in temperature. On consequent cooling and contraction, internal temperature would rise and trigger the thermonuclear reactions again. Such a body would then oscillate or pulsate weakly on the border line between planet and star. The growth rate of a planet would be strongly affected by the presence of larger objects in the same system. These larger objects, by rapidly adding to their own mass thanks to their intense gravitational field, would quickly reduce the mean density of the matter available for the growth of the planet. Usually it is the central star that is the strongest competitor for growth material. The farther away the orbit of a planet from the large central star, all other things being equal, the less the two tend to compete for growth material. Also, because the star's gravitational field weakens with distance, the local material in the neighborhood of the distant planet possesses a lower velocity than similar material in the neighborhood of a planet close to the star. Both of these factors, the lessened competition between planet and star and the lessened velocity of passing material, increase the rate at which a planet can capture material and grow. A planet distant from the star therefore may well attain greater mass than a planet orbiting nearer the star, other things being equal. In our solar system this rule is evident, for the planets more distant from the Sun, Jupiter, Saturn, Uranus and Neptune, are considerably more massive than those relatively close to the Sun, Mars, Earth, Venus and Mercury. The lower limit of planetary mass. As for the lower mass limit for planets, that is not so clearly defined. There is no change with decreasing mass that is quite so obvious as the change from non-self luminosity to luminosity, which with increasing mass converts a planet to a star. It is difficult to decide then at what level of smallness a body is not a small planet but merely a large meteoroid. By studying the relationship of the mass of non-self-luminous bodies to other characteristics, however, we may find some criterion that will allow us to define the word planet with reasonable precision by setting a lower as well as an upper limit of mass. To begin with, let's consider those bodies in the solar system that are comparatively close to the Sun and that have properties like those of the Earth in many respects. These are the terrestrial bodies. If we compare the mass and density of those terrestrial bodies for which reliable data are available, an interesting and logical pattern emerges. We find in general that the more massive the body, the more it is compressed as a whole by its own gravitational force, and therefore the greater is its density. The most massive of the terrestrial bodies is the Earth itself, and it is also the densest, 5.52 grams per cubic centimeter. Venus, which possesses a mass 0.816 times that of the Earth, is almost as dense, 5.32 grams per cubic centimeter. Mars is much smaller, only 0.1077 times as massive as the Earth, and it has a density of 4.0 grams per cubic centimeter, while the Moon, which is smaller still, only 0.01229 times as massive as the Earth, has a density of only 3.34 grams per cubic centimeter. We can carry this to an extreme by considering Earth's surface rocks. They are pulled down by Earth's gravity but are not compressed by any overlying strata of rocks. The simple pull of an outside gravitational field is small enough to be ignored, and Earth's surface rocks can be considered as bodies of zero mass. Their average density is 2.8 grams per cubic centimeter. Given the mass and density of a body, one can easily calculate the volume of that body, and from that one can further calculate its radius, the distance from the center to the surface. The densities of such bodies are then found to vary quite consistently with their radii, so that one can easily predict the density of a terrestrial body from its size alone. To be sure, the apparent density of Venus falls a trifle below the value that one would expect from the relationship. However, the actual radius of Venus is uncertain. What we see as the rim of Venus' structure is the outer limit of its cloud layer, and we are not certain what the depth of the atmosphere below the cloud layer is. The rocky sphere beneath the clouds must have a smaller radius than the one we observe, and if that smaller radius is taken, then there is little doubt that the density of Venus will be found to fall into place. Mercury is a special case. As we explained above, there is great difficulty in determining its density. The wide range of figures given for the density includes the figure that we would expect to follow from the relationship of radius and density. However, the most likely values seem to be distinctly higher than that figure. If this is not the result of errors in observation but is actually so, the irregularity may be associated with Mercury's proximity to the Sun. Since Mercury apparently keeps one face perpetually toward the Sun, the surface rock temperature on the sunny face may reach about 1300 degrees F, 700 degrees C. Temperatures of this order of magnitude accompanied by high vacuum can bring about the loss of water of crystallization from some common rock minerals, which will then become capable of more condensed packing so that their density can increase. It is also possible that the rocky material of which Mercury is composed lost gas and water through solar heat even before its aggregation into a planet. Data on terrestrial-type bodies in the solar system beyond the orbit of Mars, such as the asteroids and the large satellites of Jupiter and Saturn, are not sufficiently reliable for inclusion in this mass-density relationship. Still, what we have with the material on hand is an example of the manner in which planetary properties follow regular rules, so that planets need not be considered as unique unrelated specimens. Furthermore, from this regular relationship other characteristics can be deduced. As has been said, a regular relationship between mass and density implies a regular relationship between a planet's volume and its radius with density. From the mass and radius one can calculate the surface gravity and the escape velocity, each of which then also proves to have a regular relationship to density. However, let us follow the line of argument in still another direction. The more massive a body of a given composition, the more easily will its parts change shape or deform under its own gravitational forces. A more massive body is more dense because the compression of its inner layers increases, and this compression is a form of deformation. Small chunks of rock, in other words, can exist in almost any conceivable shape, but a large accumulation of matter is deformed under its own gravitational forces and cannot maintain an irregular shape even if one existed to begin with. On a large mass of matter, loose particles roll downhill under the force of gravity. Toward the center of the mass, where the pressures of overlying rock are greatest, even the strongest rigid materials flow like liquids until an equilibrium has been established and every particle is as close to the center of gravity as possible. An object thrown upward attains a certain height. The greater the initial velocity of the thrown object, the greater the height attained. If the velocity is high enough, then the height is theoretically infinite and the object never returns. The velocity at which this occurs is the escape velocity. For the Earth, the escape velocity is 6.98 miles per second. The situation in which every particle of a planetary body is as close to the center of gravity as possible is attained when the body takes on a spherical shape. There would be minor departures from the spherical shape because of the effects of rotation or because of differences in density among the surface material, but on the whole we could call the equilibrium shape of a sizable aggregate of matter a sphere, usually as a very close approximation. This means then that we can divide non-self-luminous bodies into two classes, those small enough to be able to maintain highly irregular shapes and those large enough to be forced into spherical shape. We can go on to apply the word planet only to the latter, and so we have our lower limit of planetary mass. It is the lowest mass at which an irregular shape is impossible and a spherical shape is enforced. The greatest possible mass of a body capable of preserving a highly irregular shape seems to be about 0.00001 that of the Earth. Such a body would have a radius of 125 miles and would be about the size of a large asteroid. For materials with particularly high yield strengths, the transition from irregular to more nearly spherical shapes may take place at slightly higher values of mass, but no known material has a yield strength high enough to maintain an irregular shape when it has a mass as much as 0.0001 times that of the Earth and a radius of about 275 miles. Before leaving them permanently, we might pause to consider some of the properties of small rock masses. A man can jump off any body having a mass less than about 7 times 10 to the 17 grams and a radius of less than 2.4 miles if we assume that he can jump with an initial velocity of 16 feet per second. A man can throw an object such as a baseball completely away from any body having a mass less than about 2 times 10 to the 20 grams and a radius of about 16 miles, assuming that he can launch it at about 110 feet per second. A rifle bullet can be shot away from any body having a mass less than about 3 times 10 to the 24 grams and a radius of about 400 miles, assuming a muzzle velocity of 2,700 feet per second. In fact, people exploring small asteroidal bodies in this size range will have to be careful about throwing or shooting for objects launched horizontally at velocities less than escape velocity might go into orbit about the asteroid. They would remain in such an orbit indefinitely and could constitute a hazard to personnel each time they schemed back in to make their closest approach. Well, then we will apply the word planet to any massive body between the mass limits 0.00001 to 10,000 times the mass of the Earth. What's more, we will not limit the term to those bodies of our solar system that are revolving about the Sim. We will apply it to bodies in this mass range whether they are revolving about the Sun or about another planet or about some distant star, or whether they are isolated in space. Within the solar system there are thousands upon thousands of small objects that do not fall within the planetary region of mass by our definition. There are, however, about 24 bodies that do. Of these, 9 are those bodies ordinarily called planets: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune and Pluto. In addition, there are 12 bodies ordinarily called satellites which nevertheless fall into the planetary mass range. These include Earth's satellite the Moon, Jupiter's 4 largest satellites Io, Europa, Ganymede and Callisto, Saturn's 6 largest satellites Tethys, Dione, Rhea, Titan, Hyperion and Iapetus, and Neptune's larger satellite Triton. Finally, there are the 3 largest known asteroids, Ceres, Pallas and Vesta. Actually, the masses of the satellites, except the Moon, and of the asteroids are not known with much accuracy, so some of those named above may have masses below our arbitrary lower limit, while a few others are borderline cases: Saturn's satellites Mimas, Enceladus and Phoebe, Uranus satellites Ariel, Umbriel, Titania and Oberon, and Neptune's smaller satellite Nereid. Gas capture and retention. As we explained earlier, there is a clear relationship between the mass and the density of the terrestrial bodies of the solar system, and the largest body we considered in connection with this relationship was the Earth itself. There are, however, 4 bodies in the solar system that are distinctly more massive than the Earth. These are Jupiter, Saturn, Uranus and Neptune. How do these fit into the relationship? The answer is that they fit the relationship very poorly, in fact not at all. The 4 massive planets, though more massive than the Earth by far, are nevertheless less dense than the Earth. They are less dense than any of the terrestrial bodies, less dense than the Moon, less dense even than Earth's surface rocks. The density of Neptune is about 2 grams per cubic centimeter, and that of Uranus is about 1.5 grams per cubic centimeter. Jupiter has a density of 1.34 grams per cubic centimeter and Saturn has one of 0.69 grams per cubic centimeter. The reason for the difference is not hard to see. The terrestrial bodies are rocky spheres without a sufficiently large gravitational field to attract much of an atmosphere, if indeed they accumulate any measurable gaseous envelope at all. The situation is different for bodies that attain a mass about 3 times that of the Earth or more. Their gravitational field is high enough to accumulate considerable atmosphere. The gases of such an atmosphere are low in density compared with the rocky sphere itself, and their presence greatly reduces the average density of the planet as a whole. Indeed, as was mentioned earlier, Venus' comparatively small atmosphere was enough to lower the overall density below the expected value. The effect becomes more extreme as the atmosphere grows more extensive. Up to a certain limit, increasing mass implies a larger and larger accumulation of gas and a lower and lower overall density. Thus Saturn, with a mass 6 times as great as that of either Uranus or Neptune, has a distinctly lower density than either of those 2 bodies. Saturn, however, is near the limit of this effect. As masses grow still higher, the gravitational field becomes high enough to compress the atmosphere to densities so high that the effect of gathering gas no longer serves to continue reducing overall density. Thus Jupiter, with a mass 3.3 times that of Saturn, is also somewhat denser. The existence of extensive atmospheres on these massive planets effectively hides the nature of their internal composition. Until more is learned about the behavior of matter under extreme conditions of pressure, reliable quantitative estimates of the internal composition of these massive bodies cannot be made, although if some assumptions are made regarding their modes of formation, some limits on their internal constitutions may be inferred. Much depends on the temperature conditions assumed at the time of formation and on the present temperatures in the upper levels of the atmosphere, for it is these upper temperatures that dictate, in part, the rate at which the gases of the atmosphere can escape from the neighborhood of the planet. A consideration of this tendency of atmospheric gases to escape from the planet shows plainly enough that the size and chemical nature of a planet's atmosphere does not depend on the planet's mass alone. One other very important factor at least is its temperature. A number of theories on the escape of planetary atmospheres have been developed in recent years. Unfortunately, the more complex of these theories require a detailed prior knowledge of the variation of temperature with changes in altitude within the atmosphere. In addition, there must be a prior knowledge of the atmospheric composition. Unfortunately, we do not have such knowledge in detail for any planet but the Earth, and theories based on this knowledge cannot be applied conveniently to generalized cases. A more useful though rough yardstick to measure the escape of atmospheric gases was first derived by Sir James Jeans in 1916. This relates the time of escape of a particular gas to such properties as the radius of the planet, its surface gravity, and in particular the average velocity of the molecules of gas in the atmosphere. To be precise, the average velocity of these molecules should be referred to as the root mean square velocity, or RMS, a phrase taken from the arithmetical procedure used to obtain this particular type of average. The higher the root mean square velocity of the gas molecules, the more difficult it is for the planet to accumulate an atmosphere in the first place, and the more readily will the planet lose an atmosphere already accumulated. For any given gas, the root mean square velocity of its molecules rises with temperature. Thus a particular planet can more easily accumulate, or retain, an atmosphere at low temperature and more easily lose it, or fail to accumulate it in the first place, at high temperature. Specifically, if the root mean square velocity of the gas in question at a particular temperature equals the escape velocity of a planet, many of the individual gas molecules will at some particular moment be bound to have velocities 2 or 3 times as high as the overall average. Some of these molecules are bound to be moving in an upward direction. Consequently, the gas will escape rapidly and permanently from the neighborhood of the planet. Even if the root mean square velocity is only 1/2 the planetary escape velocity, there will be enough molecules moving faster than escape velocity to ensure rapid loss of the atmosphere. If the root mean square velocity of the molecules is 1/3 the escape velocity, the planet's atmosphere will last a few weeks. If it is 1/4 the escape velocity, it will last several thousand years, and if it is 1/5 the escape velocity, it will last about 100 million years. Finally, if the root mean square velocity of the molecules is 1/6 the escape velocity or less, then the atmosphere is essentially permanent. No significant quantity will be lost over the life of the planet, provided its surface temperature undergoes no considerable rise at any period. For a planet to retain its atmosphere, then the root mean square velocity of the molecules of its gaseous envelope must be no more than about 1/6 to 1/5 the escape velocity. The root mean square velocities of oxygen and nitrogen in the Earth's atmosphere lie well within that limit, of course, and the Earth has no trouble retaining its atmosphere indefinitely. There are conditions under which a planet can capture or retain an atmosphere even when the root mean square velocity of the gas molecules is initially too high for the gas to be retained. The paradox is explained by the fact that no matter what the rate of atmospheric loss, the atmosphere will continue to grow if gas is arriving at a still greater rate. As the atmosphere accumulates, the planetary mass will increase, and with it the escape velocity. Eventually, the root mean square velocity of the molecules in the atmosphere will be sufficiently small in comparison to the increasing escape velocity for the rate of loss to fade off to negligible values. The rate of net atmospheric accumulation will speed up, and the gas capturing process will accelerate until it is terminated by a lack of surrounding matter. In the accumulation of such an atmosphere, the only gases that really count are hydrogen and helium. It is estimated that hydrogen makes up 90% of the material of the universe and helium 9%. All other substances make up 1% or less of the universe, and in any massive growth process their contribution can be ignored. The root mean square velocity of a gas at a particular temperature varies according to the mass of the atoms or molecules composing it, its atomic weight or molecular weight. The lower the molecular weight, the higher the root mean square velocity at a given temperature. The gas with the lowest known molecular weight is hydrogen, and hydrogen molecules, each made up of a pair of hydrogen atoms, have a higher root mean square velocity at a particular temperature than do any other molecules. It follows that hydrogen is the most difficult gas for a planet to capture or to retain if captured. Helium is composed of single atoms, each of which is twice as heavy as the hydrogen molecule. Helium therefore has a lower root mean square velocity than hydrogen and is correspondingly easier to capture. It is the more easily captured helium that in all likelihood starts the snowballing process of gas capture. Once a certain amount of helium has been captured, the increased mass and escape velocity allow even hydrogen capture to proceed rapidly, and a giant planet such as Jupiter or Saturn is the end result. This snowballing effect can produce great changes with a small initial change in mass. Terrestrial planets consist almost entirely of combinations of oxygen with the elements silicon, aluminum, iron, calcium, magnesium, sodium, and potassium. The resulting rocky material is thus made up of elements other than hydrogen and helium, and consequently out of 1% of the universe as a whole. Once helium and hydrogen begin to be collected, the solid core of a terrestrial planet may be quickly swamped. A solid core about 3 times the mass of the Earth represents the approximate minimum mass at which snowballing takes place and at which sizable atmospheres are accumulated. By the time a massive planet has accumulated gas and dust and has grown to 6.5 Earth masses, it might be half solid and half gaseous. After having grown to 14 Earth masses, it might be only 1/4 solid and 3/4 gaseous. Do Jupiter and the other outer planets possess rocky cores that are much more massive than the Earth? The obscuring atmosphere of those planets makes it difficult to say, although it would certainly seem highly probable that they do. In addition, however, there is a temperature effect that also works in favor of the outer planets as far as snowballing is concerned. What is important in this respect is the temperature of the very rarefied upper region of a planetary atmosphere, where the gas density is so low that individual atoms or molecules may travel several miles before finding other atoms or molecules with which to collide. The length of non-colliding travel is called the mean free path. This rarefied region of the atmosphere is usually termed the exosphere. In the exosphere, a very fast molecule moving vertically away from the planet has an excellent chance of moving indefinitely away from the planet without being bounced downward again by collision. It is from the exosphere then that an atmosphere is lost, and the rate at which it is lost depends on the temperature there rather than on the temperature of the atmosphere at sea level. The higher the exosphere temperature, the greater the root mean square velocity of the atoms and molecules there, and the more rapid the escape, or what is much the same thing, the less rapid the accumulation. For the Earth, the critical escape layer is apparently at an altitude of about 600 kilometers, 375 miles. The temperature at this altitude is quite variable because of the changing intensity of solar radiation, but it is quite high thanks to the far ultraviolet radiation of the Sun. Estimated temperature falls within the range of 1000 degrees Kelvin to 2000 degrees Kelvin. These are absolute temperatures, degrees Kelvin or degrees K, usually used for the higher values. If 273 is subtracted from an absolute temperature value, the equivalent temperature on the Celsius scale is obtained. The temperatures at the critical escape level in the exospheres of other planets are even less certain than is the value for the Earth. However, we can start with a temperature of 2000 degrees Kelvin for the Earth's exosphere and assume, for example, as a crude estimate, that the exosphere temperatures of other planets vary according to the distance of their closest approach to the Sun. Thus Mercury, which approaches to within 28.5 million miles of the Sun, is closer to the Sun than the Earth ever is by a factor of 3.3. Mercury's exosphere temperature then would be expected to be considerably higher than that of the Earth. On the other hand, Jupiter never approaches closer than 460 million miles to the Sun. It is farther away than we are by a factor of 5.2. Its exosphere temperature should be a great deal lower than ours. Jupiter and the planets beyond tend to undergo the snowballing effect then for 2 reasons. First, they very likely have solid cores considerably more massive than the Earth. After all, they are far from the Sun and suffered less from competition for growth material with the Sun. See page 52. Second, they have lower exosphere temperatures and for that reason can more easily capture and retain helium and hydrogen. Of these outer planets, Jupiter, the nearest to the Sun, is the most massive, Saturn farther out is less massive, and Uranus and Neptune still farther out are still less massive. This could be a reflection of the fact that in the early days of the solar system the density of growth material decreased with distance from the Sun. Light atmospheres. Of all the planets in the solar system then only Jupiter, Saturn, Uranus and Neptune had cores massive enough or exospheres cool enough or both to initiate the snowballing effect, and those four are the only planets with massive atmospheres. They are sometimes called the gas giants. Mercury does not have an atmosphere in the ordinary sense, but a very thin vapor may cling to it enough to give it what may fairly be called an exosphere. The same is true of the Moon. The remaining planets had cores insufficiently massive or exospheres too hot or both to be able to capture helium or hydrogen and thus never developed a massive atmosphere. To be sure, oxygen and nitrogen are relatively heavy gases when compared with hydrogen and helium. The oxygen molecule, composed of 2 oxygen atoms, is 16 times as heavy as the hydrogen molecule. The nitrogen molecule, composed of 2 nitrogen atoms, is 14 times as heavy. The Earth is massive enough and its exosphere temperature is low enough for it to have been able to capture these gases if they had existed in any quantity in the growth material. They did not, however. Any substance other than hydrogen or helium existed in comparatively small quantities, too small to represent easily captured material. It is doubtful then whether the atmosphere of the Earth, or any atmosphere made up of gases other than hydrogen or helium, was captured from surrounding space. It is quite likely that the Earth and all the planets other than the gas giants were first formed without an atmosphere and that it was volcanic action that then provided the primary ingredients from which the present atmosphere, and the oceans as well, developed, these primary ingredients having been originally bound physically or chemically within the rocky structure of the planet itself. It is even possible that some atmospheric constituents that normally would escape from a particular planet may be supplied by volcanic action as quickly as they escape, so that a certain concentration is always present in the atmosphere. Such constituents may also be supplied by photolysis, the breakdown of more complicated compounds into simple gases through the action of sunlight, or by radioactive breakdown. Thus, although the Earth is incapable of retaining helium in its atmosphere, small traces of the gas are present in the atmosphere and will continue to be present because the gas is continually leaking out of the soil as a result of being formed there in the course of the slow radioactive breakdown of thorium and uranium compounds. But let us return to the major products of volcanic action. According to recent studies, water is the chief component of volcanic gases at the Earth's surface, generally constituting more than 75% by volume of all gases collected at volcanic vents. The predominance of water makes it probable that in the course of the geologic ages all the water on the Earth's surface has been produced by volcanoes. It should also be mentioned that volcanic action was very likely more intense in the early periods of Earth's history. Other volcanic gases too have accumulated over the several billion years since the Earth was formed, and a number of important physical and chemical changes have taken place as a result. In the presence of water, carbon dioxide, the most common of the volcanic gases next to water, was removed from the atmosphere and converted into carbonate rocks. Other water-soluble chemically active gases produced by volcanic action, such as ammonia, hydrogen sulfide and sulfur dioxide, were also dissolved and converted into various minerals. The nitrogen and argon produced by volcanic action were retained unchanged in the atmosphere. The early atmosphere then consisted of nitrogen, argon, and whatever other gases remained in equilibrium with their dissolved forms in the gathering ocean. Once life developed and photosynthesis began, additional carbon dioxide was removed from the atmosphere by the action of the green plants and was replaced by oxygen. In the presence of a growing excess of free oxygen, any carbon monoxide or methane that had been produced by volcanic action was oxidized to carbon dioxide, which was also thrown into the photosynthetic furnace. Such hydrogen as was produced either escaped or combined with oxygen to form water. Little by little then, through reactions involving both life and non-life, Earth's atmosphere evolved its present mass and chemical composition. If volcanism is accepted as the primary mechanism for the production of atmospheres of planets that are not massive enough to capture hydrogen and helium in large quantities, then an understanding of the relationship between degree of volcanic activity and planetary mass is essential for an understanding of the general course of atmospheric evolution. Actually, our knowledge of the natural forces responsible for volcanic activity, earthquakes and mountain formation on Earth is still quite incomplete. Thus it is difficult at this time to specify general relationships between planetary mass and volcanic action, and therefore between planetary mass and the fine details of any light atmosphere that may be formed. One view is that earthquakes and volcanic heat result from the mechanical energy associated with the distortion of the crust. Distortions of the crust would be produced either by a general increase in the temperature of the interior of a planet with subsequent expansion, or by a general cooling with subsequent contraction. On the whole, the higher the internal temperatures, the greater the changes either way and the more pronounced the volcanic action. The high interior temperatures of the Earth are due apparently both to gravitational compression and to the accumulation of heat released by radioactive materials such as uranium, thorium and potassium-40. The last is a comparatively rare isotope of the common element potassium. Radioactivity is apparently a more important contributor to internal heat than is gravitational compression. A planet smaller than the Earth would tend to accumulate less heat through gravitational compression during the period of formation. Then too, what heat was formed either through gravitational compression or through radioactivity would escape more readily from a smaller planet than from a larger one. To see the reason for the more rapid heat loss, consider that the ratio of surface area to volume increases as an object of a particular shape decreases in size. A small spherical planet has more surface area for its mass than a large spherical planet. If a sphere is reduced to 1/8 its former mass, its surface area is reduced by only 1/4. By reducing the sphere in this fashion, the ratio of surface to mass has doubled. Since heat is lost through the surface area, then a small sphere would lose its heat at a more rapid rate than a large sphere, for it would have more surface area, in proportion, through which to lose the heat. Small planets might also tend to have less concentration of metals toward the center, and since metals are good conductors of heat if they are spread more evenly through the planet as a whole, and especially its outer regions, is a better heat conductor. As a result, internal heat is lost more rapidly. In short, there is every reason to think that small planets have lower internal temperatures than large ones, and consequently have less volcanic activity and less gas formation than large planets. It is not surprising then that Mars, considerably smaller than the Earth, also has a considerably thinner atmosphere. The atmospheres of Earth and Mars differ not merely in total mass and in chemical composition. The Martian atmosphere lacks more than a trace of oxygen. They vary in another and more subtle fashion. The manner in which the density of a planetary atmosphere varies with altitude above the surface depends to a great extent on the strength of a planet's gravitational field. A large planet with a high surface gravity compresses the lower layers of its own atmosphere under the weight of the upper layers. The density of the atmosphere therefore changes markedly with changes in altitude, dropping off rapidly with height. A small planet with a low surface gravity has a smaller compressing effect on its atmosphere, which therefore shows a more gradual decrease in density with increased altitude. On Earth, for example, the atmospheric density drops by a factor of about 2 for each 17,000 feet of ascent above the surface. On a larger planet having the same atmospheric molecular weight and temperature conditions, this halving of density would take place in altitude intervals of less than 17,000 feet. On a smaller planet, the density halving would take place in altitude intervals of more than 17,000 feet. A large terrestrial planet might therefore be said to have a hard atmosphere and a small planet a soft atmosphere. For example, Mars has a softer atmosphere than Earth has. This relationship between size and density change in the atmosphere has a great bearing on the ease of entry of a space vehicle into a planet's atmosphere. Entry into the atmosphere of a small planet such as Mars can be achieved with less rigid restriction on angle of entry and with lower accelerations imposed on the passengers than entry into the atmosphere of larger planets such as the Earth. To summarize then, we see that planets can fall into 3 atmospheric classes: 1. Planets without measurable atmospheres. Such planets have a gravitational field too small to retain even those common gases with the most massive molecules. Perhaps most planets fall into this class since in all likelihood there are more small planets than large ones and a small planet has a small gravitational field. The best known examples include Mercury with its unusually high exosphere temperature and the Moon, which has a lower exosphere temperature than Mercury has but also possesses a distinctly smaller mass and consequently a lower escape velocity. Two planets with light atmospheres. These have gravitational fields too small or exosphere temperatures too high to capture hydrogen or helium and consequently do not undergo the snowballing effect and do not collect massive atmospheres. However, their gravitational fields are large enough to retain moderately heavy gases such as nitrogen, oxygen and carbon dioxide where these are produced by volcanic action. The one habitable planet of the solar system, the Earth, falls into this class. Venus is another member. Mars is too small to be an efficient gas retainer or to have the extent of volcanic action probably found on more massive planets such as Earth and Venus. Nevertheless, it too retains an atmosphere, thinner than that of the Earth or Venus, aided by its exosphere temperature which is lower than that of Earth or Venus. Three planets with massive atmospheres. These have exosphere temperatures low enough and rocky cores massive enough to allow them to initiate the snowballing effect. The atmospheres collected are composed largely of helium and hydrogen, and the four known examples of this class are Jupiter, Saturn, Uranus and Neptune. The oblateness of rotating planets. Most of the discussion up to this point has been concerned with the properties of massive bodies that are not rotating rapidly. The rate of rotation, however, is an important property of a planetary object affecting its shape, surface, gravity and habitability. In a consideration of general planetary properties, the effects of rotation cannot be ignored. The shape of a rotating body isolated in space depends on its rate of rotation, its average density and the distribution of mass within the body. A rotating body experiences a centrifugal effect which produces an upward pull countering part of the downward pull of gravity. The strength of this centrifugal effect on a particular portion of the planet's surface varies according to the velocity with which that portion moves. In the case of a planet rotating about an axis, the surface does not move at all at the poles but moves with greater and greater velocity as the distance from the poles increases, reaching a maximum of course at the equator. Thus on Earth the velocity of rotation for an object on the surface at Anchorage, Alaska or Leningrad, USSR, 60 degrees north latitude, is 520 miles per hour. At Peking, China or Philadelphia, Pennsylvania, 40 degrees north latitude, or at Wellington, New Zealand, 40 degrees south latitude, it is 800 miles per hour. At Bombay, India or Mexico City, Mexico, 20 degrees north latitude, or at Rio de Janeiro, Brazil, 20 degrees south latitude, it is 975 miles per hour. Finally at Singapore, Malaya or Quito, Ecuador, on the equator, it is 1040 miles per hour. The increasing centrifugal effect in a rotating planetary body lifts the very structure of the planet upward against gravity, the upward lift being greatest at the equator. In this manner an equatorial bulge is formed and the planet, instead of being a sphere, is an oblate spheroid. For an oblate spheroid the equatorial radius, the distance from the center of the planet to a point on the equator, is greater than the polar radius, the distance from the center of the planet to one of the poles. Naturally, as a given body is caused to rotate more and more rapidly, its equatorial bulge grows so that it departs more and more from a true sphere and becomes more and more oblate. The oblateness of a planet is defined as the difference between the equatorial radius and the polar radius divided by the equatorial radius. For instance, Earth's equatorial radius is 3,963 miles while its polar radius is 3,950 miles. The difference is 13 miles, and if that is divided by 3,963 we find Earth's oblateness to be 0.0033 or about 1 in 300. The actual oblateness depends not only on the velocity of rotation but also, as we said above, on the density of the planet and the distribution of mass within it. In fact, it is possible to calculate what the oblateness ought to be for planets rotating at a particular velocity according to two different sets of assumptions, one assuming the planet to be of uniform density throughout, and 2 assuming all the mass of the planet to be concentrated at the center. The first assumption, uniform density, yields markedly higher values for oblateness than does the second, concentrated mass. For instance, if the Earth were of the same density throughout, its oblateness should be about 1/250th, if its mass were all concentrated at the center it would be only about 1/500th. The fact that the Earth's oblateness is intermediate between these two extremes indicates, as we know, that the Earth is not uniformly dense and that its mass is concentrated toward the center, but that the mass is not all at the center. The other oblate bodies of the solar system also show values intermediate between the theoretical extremes, indicating that limited concentration is true for them as well. The most oblate planets of the solar system are Jupiter and Saturn. Despite their large size, their periods of rotation are considerably shorter than that of the Earth. Jupiter rotates in 9 hours 50 minutes, Saturn rotates in 10 hours 15 minutes. While a point on the Earth's equator moves at a velocity of 1040 miles per hour, one on Jupiter's equator, at the level of the cloud layer that is, since that is all the surface we see, moves at 28,500 miles per hour, and a point on Saturn's equator moves at 23,000 miles per hour. The equatorial regions on those giant planets are lifted much higher than are those of the Earth, even against the stronger gravitational fields on Jupiter and Saturn. Jupiter's equatorial radius is nearly 3,000 miles longer than its polar radius, while in the case of Saturn the difference is nearly 4,000 miles. The oblateness of Jupiter is 0.062 or about 1/16, while that of Saturn is 0.096 or about 1/10. Earth's oblateness is so small that seen from space its shape would not depart visibly from a sphere. Jupiter and Saturn as seen in a telescope, however, are clearly non-spherical, bulging amidships quite visibly. The oblateness values of Uranus and Neptune are not known with precision. The oblateness of Uranus lies between 0.05 and 0.07, 1/20th to 1/14th, while that of Neptune lies between 0.02 and 0.033, 1/50th to 1/20th. Both planets revolve more rapidly than the Earth does, despite the fact that they are larger than the Earth, and both are not surprisingly considerably more oblate than the Earth. Mars has a period of rotation about the same as that of the Earth, for it rotates in 24 hours 37 minutes. Mars is a considerably smaller body, and a point on its equator moves only 550 miles an hour, so it is not surprising that Mars has an oblateness too small to be measured precisely. The oblateness has been calculated, however, from slight changes in the orbits of Mars' tiny satellites, and seems to be 0.0052, about on 200th. This oblateness is greater than that of the Earth despite the slower velocity of Mars' equatorial region, because Mars has a lower density than the Earth and is less compressed toward its center. Mercury, Venus and the Moon, all with very slow periods of rotation, have no measurable oblateness. Naturally, the surface gravity on an oblate spheroid would vary with position on the planet. A man standing on the Earth's equator would be farther from the center of the Earth than one standing at the North Pole, and the force of gravity would be consequently weaker at the equator. The effect is not marked. A man weighing 200 pounds at the North Pole, or the South Pole, would weigh only 199 pounds at the equator if all measurements were corrected to sea level. The effect would be much greater, however, on planets as oblate as Jupiter or Saturn. On Saturn, gravitational attraction at the equator, at cloud level, which we again point out is the only surface we can see, would be only 4/5 what it was at the poles. A 200-pound weight at the Saturnian pole would weigh 160 pounds at the Saturnian equator. For the planets of our solar system, a very interesting relationship between mass and rotation rate strongly suggests that these factors are not independent of each other. In general, the greater the mass, the more rapid the period of rotation. Thus Jupiter, with the largest mass of any of the planets, also has the shortest period of rotation, 9 hours 50 minutes. Saturn, with a smaller mass, rotates in 10 hours 15 seconds. Uranus and Neptune, with masses still smaller, rotate in 11 or 12 hours. Neptune's period may be as long as 15 hours. Finally, Mars, which is far smaller than any of the outer planets, rotates in 24 hours 37 minutes. This relationship of mass and rotation period can be made a rather simple one by the proper mathematical treatment so that the rotation period of a body of given mass can be easily predicted. The Earth itself, as it turns out, has a longer rotational period than one would expect from this relationship. After all, it is 10 times as massive as Mars, yet it rotates in about the same time. If the relationship displayed by the data obtained from the other planets held for the Earth, it would be rotating in 15.5 hours rather than in 24. However, it seems quite clear that over the ages the Earth's rotation period has been slowed by the tidal effects of the Moon. The other planets, Mars, Jupiter, Saturn, Uranus and Neptune, do not have any satellite as large in relation to themselves as the Moon is in relation to the Earth. They therefore have not suffered a comparable slowing effect. The Moon itself suffers a slowing effect even greater than that suffered by the Earth. While the Earth is affected by the Moon's gravity, the Moon is affected by the Earth's 81-fold greater gravitational field. The Moon's rotation has been slowed to a complete standstill with respect to the Earth so that one of its sides always faces us. Its rotation with respect to the Sun, however, has not stopped. Its solar day is about 700 hours, which is equal to its period of revolution about the Earth, 29, 2 days or 1 synodic month. The period of rotation of Mercury has been drastically slowed by the Sun's tidal effects and is now equal to 88 days, a period equal to its time of revolution about the Sun. The period of rotation of Venus is not known because of its featureless and obscuring cloud cover. In 1962, data obtained by reflecting radio signals from the surface of Venus were interpreted as indicating that Venus' period of rotation equaled its period of revolution, 225 days. The indications are not conclusive, however, although we may be quite sure that Venus does rotate quite slowly as a result of the Sun's tidal pull. Were it not for the slowing effects of external bodies, Venus might be rotating in a period of 16 hours. Mercury in a period of some 30 hours and the Moon in one of some 40 hours. Spacing of planets in the solar system. The regular spacing of the orbits of the planets of the solar system has interested students of astronomy ever since the planetary orbits were first established and measured with accuracy. Prior to the mid-19th century, much significance was attached to the Titius-Bode law of orbital distances. This rule was expressed by a particular series of numbers derived as follows: starting with the number 3, follow it by additional numbers each twice the preceding number. Place a 0 at the beginning of the list and the result is 0, 3, 6, 12, 24, 48, 96, 192, 384, 768. To each number in the series starting with the 0, 4 is added. The new series thus produced is 4, 7, 10, 16, 28, 52, 100, 196, 388, 772. If one sets Earth's distance from the Sun equal to 10, the average distances of some of the other planets from the sim, including that of Ceres, the largest of the asteroids, in proportion are as follows: Mercury 3.9, Venus 7.2, Earth 10.0, Mars 15.2, Ceres 28, Jupiter 52, Saturn 95, Uranus 192. In the 1840s, these were the only planets known, and the manner in which their relative distances fit the Titius-Bode law was very impressive. Neptune, however, is at a distance of 301 and Pluto at an average distance of 395, where the rule predicts 388 and 772 respectively. With the discovery of Neptune in 1846, therefore, the rule ceased to be regarded as anything but an interesting coincidence. Another way of describing the planetary spacing is to make use of theoretical considerations of orbital stability and of the existence of forbidden and permitted regions. In general, the concept may be summarized as follows: each planet as it moves in its orbit creates a broad band centered on that orbit, a forbidden region, within which no smaller planet can exist in a stable orbit. If a smaller planet somehow found itself in the forbidden region, the gravitational pulls of the nearby larger planet would in a short time, astronomically speaking, move it out of the region. The size of this forbidden region depends in part on the distance of the planet from the Sun, so that the forbidden regions of successive planets tend to increase in width as one moves outward from the Sun. Thus the width of the forbidden region associated with Jupiter is 250 million miles, whereas that associated with Saturn is 350 million miles. You would not expect the forbidden regions of adjacent planets to overlap, and Jupiter and Saturn are indeed spaced far enough apart to prevent this. In general then, as one recedes from the Sun, the planets are spaced farther and farther apart as the forbidden regions widen. The increasing numbers of the Titius-Bode law reflect this, and that is why the law seemed to work at first. The width of the forbidden region also increases with mass, so that Jupiter's forbidden region is larger than it might be, judging only by its distance from the Sun. Uranus and Neptune, being distinctly smaller than Jupiter and Saturn, have forbidden regions that are correspondingly smaller than they might be, and this may account for Neptune's being closer to the Sun, and hence to Uranus, than would be predicted by the Titius-Bode law. The width of the forbidden region also increases with the eccentricity of a planet's orbit, that is, the manner in which the shape of that orbit deviates from a perfect circle. For most planets this deviation is quite small and can be disregarded. Mercury's orbit, however, and even more so Pluto's, are distinctly elliptical. For that reason both Mercury and Pluto have forbidden regions that are much wider than one would expect from their mass and their distance from the Sun. The spacing of the planets about the Sun can then be viewed as resulting from the tendency of each planet to stake out a territory for itself. The first 8 planets, Mercury, Venus, the Earth, Mars, Jupiter, Saturn, Uranus and Neptune, are all situated so that no forbidden regions overlap. Pluto does not follow this rule. Although Pluto's average distance lies outside Neptune's forbidden region, Pluto's orbit crosses into it at Pluto's nearest approach to the Sun. Since Pluto's orbit is markedly elliptical, it approaches far closer to the Sun at one region of the orbit than it would if its orbit were at the same average distance but nearly circular. Pluto's orbit is clearly unstable for this reason, and the situation may even foreshadow an eventual catastrophic alteration of Pluto's orbit by Neptune sometime in the distant future. Indeed, it may be that Pluto's existence as a planet is the result of such a catastrophe in the distant past. Some astronomers suspect Pluto to have been a satellite of Neptune at one time. In some fashion it came to be thrown clear, but it has retained a highly unusual orbit, invading its ex-companion's forbidden region ever since. The gaps between the forbidden regions are not always as narrow as they might be, so the forbidden regions take up only about 50% of all the planetary space of the solar system. Notably, there is a wide gap between the forbidden regions of Mars and Jupiter, and within this gap the asteroids circle. There are also interestingly wide gaps between the forbidden regions of Uranus and Saturn and between those of Neptune and Uranus, where small orbiting objects, as yet undiscovered, may well exist. This pattern of regularity of the solar system should also be found in other planetary systems.